examples. K is Q. S consists of the Schmidian place, the only one, plus periodic places associated to the primes P1, PR. Then OS is a ring obtained by inverting the primes. Which is also the ring generated by 1 over 12. So for instance, this is a ring of S. The group of S units OS times is the group of units of OS. Which means the element of K which have absolute value exactly equal to 1 for every place outside S. And in this case, this example of S cross is the group generated by -1 and P1 PR. So P1 P1 where back P1 is integral. In general, the Dirichlet theorems says that OS cross is finitely generated of rank equals cardinal of S. So here you have R plus 1 place, the rank is R. Now, if you have point P in n-dimensional projective space, okay, D as x naught x n, where each xi is an element in K, and for every place U, we have a well-defined reduction map. Residue fields of K minus modulo the maximal ideal, and mu is okay. Absolute value is strictly less than 1. This is finite field. Simply can use coordinates such that they are integers and not all belong to the maximal ideal, and you reduce the coordinates. Now I'd like to define the notion of an integral point on an algebraic variety. So suppose that V or calling V tilde is a complete projective algebraic variety defined over the number k. So suppose that V tilde is contained in a projective space Pn. So suppose V tilde is contained in a projective space Pn, and it's defined in Pn by a system of algebraic equations defined over K. Now, for we take an algebraic subset D.
Excuse me?
Yes.
Is the Pn of OK or K in this reduction one? You have taken K to Pn of OK by N.
Change the scalars and make it to OK.
Well, you can take a point with coordinates in K, but since coordinates are defined up to constant, you can suppose. Yes, actually, I will explain in a moment that Pn of K is the same thing as Pn of OK. So, taking algebraic subset, we say that a rational point P tilde minus D, okay. So, a rational point of V tilde which does not belong to D is, we say SD integral or S integral with respect to the subset D if for no place mu outside S, P reduces modulo mu to a point in D. So letting D be the open subset V tilde minus D, we denote by POS the set of S integral points. So SD. Actually, this notion only depends on the open set V and not on its completion V tilde. Now I'll show how this notion of integrality is connected with the naive notion of integral points on an affine variety. Consider, for instance, B equals the affine line A1. So its natural completion, B tilde, is the projected line B1. And A1, the affine line, is embedded into the projected line by sending the point X to the point X1, projected coordinates. The complement of V in B tilde is subset D consisting of just one point. It's the point 1, 0. And 1, 0 also called the point infinity of the line. Now, if point X is equal to a point, then X1, that X1 is this way. So this is a projective point which is never congruent to 1, 0 modulo any prime editor. Any non-zero. Well, any prime. So well. On the contrary, take a rational number which is not an integer, for instance, 2/3. This is a point in A1 cube. It's not an integer. And if I embed A1 into P1, 2/3 is sent to 2/3 1, which is the same as 2, 3. Now I've written my point with coprime integral coordinates, and this is congruent to the point 2, 0, which is the same as 1, 0, which is the point at infinity, modulo 3. So this is the reason why it's not an integer. So we obtain that integral points on A1 are just integral points in the naive sense. And the same holds if B is an affine variety. Affine variety means closed subset of AN, and we can embed AN into EN in the canonical way by adding one coordinate, and so let B tilde be the closure of B in Bn. Let D be the complement, B tilde minus B, and then the integral point BOS are just the solutions in S integers to the system of equations defining V A. So the naive definition of integral points coincide with the more involved one I've just given, but the new one is more general. We can speak of integral points even on varieties which are not affine, so they are not defined by a system of equations in AN. For instance, we can take and consider the example where we take V with the empty set, so that V is the same as V tilde. So V is projective. I don't eliminate anything from the projective variety tilde. And what are the integral points on V? Well, there are rational points which satisfy a further condition which is empty now. They do not reduce to the empty set. It's clear. So these are just all rational points. For instance, in the projective space, rational and integral points are the same. But we can also work on varieties which are neither projective nor affine. For instance, if we remove one point from a smooth surface, we obtain a variety which is neither complete nor affine. And it makes sense to speak of integral points in this case. I show more examples. For instance, consider we have already seen P1 minus 1 point. Let's see P1 minus 2 points. So fixed coordinate, consider 0, infinity. So 0 is the point 0, 1, and infinity is the point 1, 0. So this is B. What is B? B is isomorphic to the group variety GM, multiplicative group. The one-dimensional curves. So if you remove the infinity, you obtain the affine line. If you remove the origin from the affine line, you obtain multiplicative group. And what is the set BOS? So GMOS. Can write point X GM, and we view it as X1 and P1. The fact that X is integral with respect to infinity means, as we have just noticed here, that X is an integer in the usual sense, so it's an SE. It does not reduce to 1, 0 modulo any place. And the fact that X1 does not reduce to 0, 1 modulo any place outside S means that X belongs to no prime ideal of the ring OS. So X is a unit. So finally, GM S, the group of S integral points in the group variety GM, is the set of S units. And of course they form a group. Now consider another example, B1 minus 3 points. To make a canonical choice, consider the point 0, 1, infinity. So we have one further integrality condition that the point in question never reduces to 1 modulo any prime. So x, I'd like to call x u, because it's a unit, and u does not reduce to 1 modulo any prime ideal. Which means that u minus 1 does not belong to any prime ideal, so u minus 1 is a unit. I call u minus 1, prefer to call it minus b, but b is a unit. And so obtain u plus v equals 1. So S integral points, B is B1 minus 3 points. So S integral points on B correspond bijectively to solutions in units to the equation u plus v equals 1. And this equation can be viewed as an exponential equation, and I've written it as a linear equation, but the unknown units, since the group of units is a multiplicative group and is finitely generated, I can turn this equation into an exponential one. For instance, consider the ring of integers. OS is z1 over 30, so that 2, 3, and 5 become units. So the group of S units formed by element of this form, plus or minus 2 to the a, 3 to the b, 5 to the c. So for instance, every solution to 2 to the a plus 3 to the b equals 5 to the c defines, gives u equals 2 to the a 5 minus 3, and b equals 3 to the b 5 minus c, and solution to this equation. So solution to this exponential Diophantine equation can be viewed as the integral points on a certain algebraic variety. Actually, such equations always have only finitely many solutions. First two examples of A1 and GM. Integral points are Zariski dense, at least if you allow a finite extension of the OS. So if S has at least two elements. So if K is not Q of the imaginary quadratic field and S reduced to only Archimedean places, then the group OS cross is infinite, so it's a risky then set of equations. While here it can be proved, it's the theorem due to Siegel and Mahler, that there are only finite solutions. Now I show some examples in higher dimensions. So consider, for instance, P2. So B tilde is P2. We already said that if we remove a hyperplane, we obtain an affine variety, and the integral points are just integral points in the 96. Here hyperplane means a line. So P2 minus one line is A2, and the integral points are just points x, y, z. So suppose that the line z equals 0. So z a unit. So if you let small x with capital X over z and y and small y is capital Y over z, then you obtain pairs x, y, OS cross OS. So the integral points on P2 minus one line are just pairs of integers in the usual sense. Now, what happens if we remove two lines? You can choose coordinates such that the lines are z equals 0 and so for instance y equals 0. So we have to consider the pairs of integers x, y, such that the point x, y never reduces to the line y equals 0. Never. To y equals 0. So it means that y is a unit. So we obtain OS cross OS. This is the set of integral points on the complement of two lines in P2. And if we consider three lines in general positions, then suppose the lines are z equals 0, x equals 0, y equals 0, and we obtain so integral points x, y such that both x and y belong to no prime ideal, so they are units. We obtain OS cross OS. And actually geometrically, P2 minus three lines in general position is isomorphic to GM cross GM. So if you remove the line at infinity, you obtain the plane, the affine plane. If you remove two more lines, suppose they are the coordinate axes, so you obtain pairs of non-zero scalars, so GM cross GM. And now what happens? Four lines in general position. So we can suppose the lines are z equals 0, x 0, y 0, plus y okay, so now we obtain the point. The first three integrality conditions give point OS cross times OS cross, and xy corresponds to x y 1 and x, we want that x plus y minus 1, so you take that on the other side, never reduces to 0. So x plus y minus 1 is a unit. Call it minus w, and I like x, change the name, call it u because it is a unit, and v is also y is also a unit, so I call it v, and so I obtain the equation u plus v plus w equals 1 to be solved in units. So integral points on the complement of 4 lines in general position in the plane correspond bijectively to S-unit solutions of the linear equation u plus v plus w equals 1. And is a theorem called the S-unit equation theorem. It was proved in a particular case by Dubois and in general case by Evertsen, and independently by Schlickeweil and van der Poten. There are only finitely many non-trivial solutions or non-degenerate solutions. Let's call it non-trivial solutions. And trivial solutions are those for which one of the 3 unknown equals 1 and the other 2 eliminates each other. So solutions like 1 d 1 d minus d, so this is u w, where d is a unit, and you can terminate. So you have 3 infinite families of trivial solutions, and outside these 3 families you have only finitely many solutions by a deep theorem, which is one of the first important applications of the subspace theorem. It was proved in the 70s, in particular case, and in the 80s. I'd like to show by a picture that the 3 infinite families of trivial solutions can be easily understood from the geometry of the complement of 4 lines 2. So let us draw 4 lines. Position. We have to consider the plane minus these 4 lines. If we join 2 singular points of this configuration, you obtain this dotted line on the plane with a line on the plane is isomorphic to P1. If we remove from this line the points at infinity, so the points in this configuration of 4 lines, we have to remove just 2 points. While a generic line intersects this configuration of 4 points, there are certain special lines, like the one I drew, that intersect only at 2 points. So this dotted line is P1 minus 2 points, and so it is geometrically isomorphic to Gm. And Gm contains infinitely many integral points which correspond bijectively to S units. So every S units give an integral point in this line, integral with respect to these 2 points, and so we obtain infinite families of this kind. You see that trivial solutions correspond bijectively to units, which means points Gm. And there are 2 more dotted lines here, and another one is here. Exercise in algebraic geometry to prove that there are basically, if B is the complement of 4 lines, there are up to 2 endomorphisms of Gm, 3 non-constant maps from Gm to B. So there are 3 curves on the complement of 4 lines, which are parameterized by Gm, and they are just the 3 lines. So you think that there are 3 trivial families of solutions, 3 kinds of producing in a trivial way infinitely many solutions, and the deep theorem of S-unit equation says that apart from these solutions, there are only finitely many more. So let's see what happens if we remove a conic positions. So can suppose that one line is 0, first line, and x equals 0, second line. So the integral points with respect to these 2 lines are pair of u, y, so it's x, y, but that's should be called u because it's a unit, and y is any integers. These are integral with respect to the 2 lines. Now conic, for instance, y square equals x squared plus 1, this is conic. And so you obtain that y square minus u square minus 1. This never reduces to 0, so is a unit. And so you obtain the equation y square equals u square plus b plus 2. And actually, you say that here I have u square, but basically units are always squares in the sense that since the group of units is finitely generated, the quotient of the group of units modulo subgroup of squares is finite. So up to enlarging the field, you can reduce also to the equation. The equation y square equals u plus b plus 1. So, so the problem is finding two units such that the sum plus 1 is perfect square. For instance, you obtain equation of the form y square equals 2 to the a plus 3 to the b, 5 to the c plus 4, for instance, to be solved. In a, b, c natural numbers. This is an example of an exponential Lafontaine equation whose solutions give integral points on that parameter. And it's an open question that all equations of this kind have only finitely many solutions. Apart from possible trivial solutions, which in this case do not exist in these particular equations, trivial solutions may be obtained in this way. If you take t, the units, you consider the identity t plus 1 square equals t square plus 2t plus 1. So consider this equation.
But why n or z here?
Pardon?
ABC are in integral.
Oh, for instance, we can take natural numbers. Solutions of this kind, in particular, with no points. So you have a solution of this equation with u equals t, v equals 2t. You can say this infinite families in a similar way. Dotted line, this line, which geometrically corresponds to a curve parameterized by G. Another example is the complement of a conic and two lines not in general position. So the two lines intersect on the conic without tangent. And so in this case, suppose the first line is z equals 0. The second line is x equals z, and the conic is xy equals z squared, for instance. So in this case, integral points correspond to integers x, y. Such that so we call that this corresponds to x, y, 1. So x does not reduce to z means x does not reduce to 1. So x minus 1 is a unit. And then we want that x, y minus 1 square is a unit, and x is u plus 1, so u plus 1 y equals to v plus 1. So you think y is v plus 1 or u plus 1. And in this case, we have a divisibility condition. We want that this ratio be an integer, so the problem is u plus 1 divides v plus 1. So integral points in this case correspond to pairs of units satisfying this divisibility condition. And it's easy to see that they form a Zariski-Dense set in the plane. For instance, we take Z 1 6, so 2 and 3 are units. Take V of the form minus 2dn plus minus 2dn, and U of the form 3dn. So the problem is 3dn plus 1 divides 1 minus 2 to the n of 2 to the n minus 1. Same. Okay, so 2 to the n convert to 1 modulo 3 to the n. Well, so this is over the integers, so probably 3 to the n plus 1 in z. So it's not possible in z, but in z plus 6 it's possible. So we have to write 3 to the n plus 1 as power of 2 multiplied by of the integer, and then take 2 to the n convert to 1 modulo q in usual ring of integers. So 2 to the n minus 1 over 3 to the n plus 1 will be power of 2 multiplied by an integer. This is a unit in the ring, this is an integer, so the ratio is an integer. So there are infinitely many solutions, and actually it's a Zariski-Dense set of solutions. Well, Now, just say some words about the analogy. With complex analysis, complex geometry. And so in the program of the course by Gaspari that this analogy will be explored. He will introduce nonlinear theory. I will just restrict to giving some statements without any idea of the proof. In this case, an integral points in a variety defined over a number field should correspond, according to this analogy, with the entire curves. So now B is defined over C. You can consider holomorphic maps from C to the set of complex points, which is an analytic variety, analytic manifold, and these are complex analytic. Maps, which are also called entire. So you can also see F as a map from C to the completion of the tilde, omitting the divisor at infinity, omitting the algebraic subset. D, we call that D is a complete variety minus divisor D. So an integral point is a rational point which never reduced to D modulo any prime, and an entire curve is an entire curve in the complete variety which never touches the part at infinity. And it is conjectured that there is an equivalence between these two conditions. First, B of S is Zariski dense, for a suitable ring of S integers. Condition there exists F C C type curve with the Zariski dense image. All the examples are shown. This analogy holds, but the penultimate example, so the equation y squared equals u plus b plus 1, said that this is an open problem in arithmetic to prove the generality of solutions, while in complex analysis it has been proved a few years ago So it has been proved that if U and B are entire, never vanishing functions, such that U plus B plus 1 is a square in the ring of entire functions, which means geometrically that you have a rational, you have an entire curve on the complement of the conic and two lines. Then either U or B is constant, or there is an identity as the one I wrote. So U is B square and B is 2T, or one is trivial identity. This is a recent result of Noguchi, Winkelmann, and Yamanori. For curves, for dimension 1, we have a clear picture, both in the arithmetic and in complex analytic setting. Now I'll give results. Curves. Dimension B equals 1. The following situation. We're supposed to simplify that T tilde is moved. So B is topologically classified by two invariants. One is the genus G of tilde, and second invariant is let's call it R, cardinality of D. D now is a finite set of points. So B tilde minus finite set, which might even be empty. Now the theorem, which is due to Siegel, in particular case, quantum general, says the following: if B OS is Zariski dense, which is the same as infinite, irreducible variety of dimension 1, Zariski dense means infinite, then G equals 0 and R is less than 2, or less than or equal to 2, or G equals 1 and R equals 0. Contrary, if one of these conditions satisfied, so one pair of conditions satisfied, so genus is 0 and that was 2 points at infinity, or the genus is 1 as the curve is complete, so we don't move anything. There exists OS, which means categorical integers, such that the OS is infinite. So let's see what it means. means that the rest can be infinite only in the following cases. So genus 0 and consider no points at infinity, so B is P1, in which case rational and integral points are the same. So rational points on P1 are substitutes. Second case, genus 0 and 1 point at infinity, so A1, the affine line. In this case, the integral points are integers in the usual sense, and they are infinite. Third case, genus 0 and 2 points at infinity, so we said that the variety is the group variety GM. Again, integral points can be in the curve. You take an algebraic point of infinite order in the sense of the group law on the elliptic curve. So you take for K the number field sufficiently large to contain the coefficient of the equation for B and the coordinates of this point of infinite order, and over this field you have infinitely many integral points. Actually, it's not completely obvious that there exist algebraic points of infinite order. And so in each of these cases, not only there can be infinitely many points, but really there are if the ring is sufficiently large. So in other words, this theorem is best possible. It's classification of curves with infinitely many integral points and complex analytic analog if V is a Riemann surface and F C to V is holomorphic to constant, then B belongs to that list. And vice versa for each one of these Riemann surfaces, there exists an entire non-constant map towards that Riemann surface. Clearly, there are entire holomorphic map to P1, to A1, which is the same as C, to GM, which is C star, that is the exponential map, and to an elliptic curve, which is a complex torus. So the universal cover is an entire non-constant map. On the contrary, if you remove from P1 3 or more points, there are no entire curves on the complement, which is Picard theorem. An entire holomorphic function cannot omit 0, 1, and infinity. And the same if you take a Riemann surface of genus at least 2, and its universal cover is the disk. So the genus of V is 2. You obtain delta is the disk. This this is the universal cover. Every map from C to B lifts to a map from C to delta because C is simply connected, and an entire function which is bounded is constant. So this map will also be constant. So this is the analog of Falken's theorem that rational points on V are finite. Okay, I think I can stop here for today.
So what do you propose to do with the plan of lectures?
I propose to explore the case of surfaces. So I will introduce the tools from Diophantine approximation. So I will speak about the subspace theorem without proof. Then I will give applications. Well, first I'd like to prove Siegel theorem, which is the affine case of this theorem when R is non-zero. And I will prove Siegel theorem in detail, starting from the subspace theorem, and then I will explore many examples for surfaces.
So you introduce subspace theorem also?
So next time I will introduce subspace.